Okay, let's talk about center of mass. Center of mass. To calculate the center of mass of a system of particles, what we do, if we just think of in one dimension, if you think of a mass here, m1, and I'll have another mass here, m2, which is much bigger. If we think of that, the center of mass of that system of objects is going to be closer to m2 because it's really sort of a geometrical weighted center location of the mass. So the center of mass might be here. The way we calculate it is we pick a zero. I would ordinarily pick a zero through m1, but I'm going to pick a zero right here. And I'm going to say that is the distance to m1, and this all the way over to m2 is the distance to the center of m2. And the way we find the center of mass is we say x center of mass is equal to the mass times the distance plus the mass times the distance divided by the total mass. So we divide by m1 plus m2, in other words, the mass of the system. So it's the distance times the mass for each of the objects added together. So we would end up with m1x1 plus m2x2 divided by m1 plus m2. And that's the way we calculate the location of the center of mass. And you can see if m2 is much bigger, than m1, in other words, if that first term isn't there, it's really x2 times m2 over m1 plus m2, which ends up being basically 1. So the closer m2 gets to infinitely larger than m1, the closer the center of mass gets over there. So that's the x center of mass. If we want to do the y center of mass, it's the same sort of thing in the y direction. And the way we write this, the notation we have in general for this, for discrete objects, is the sum of mi, xi, divided by the sum of mi. And again, this bottom is just the total mass of all the objects in the system. And this is the distance to each one times the mass of each one. Okay, let's say we've got a solid object. If we think of that object, if we think of every molecule in that object, and we say every molecule in there has a mass dm, then if we want to find the center of mass of that object, let's declare the end to be 0, position 0, x equals 0, and let's say the end is x equals L, then really what we're doing is we're adding up all the dm times x, okay? X is the distance to this dm, right? And we keep doing that to get our top. And at their bottom, all we have to do is add in all the dm's. So it really ends up being the integral over the entire length of dm times x. I'm going to write it as x dm, just because I like to see that differential notation at the end. And then divided by the sum over that entire length of all the dm's. Okay? So in other words, we're saying at every distance x, how much mass is there? And we're adding all of those up over L. The bottom's a lot easier to see. We're just saying, let's add up all the dm's over that entire length of that object. So that's how we would integrate to find the center of mass of as we're going to find a more uneven object. So let's do that. First, let's start with an even object. Let's pretend it's just a bar, and we're going to say this is very thin, okay? So how this might be specified is by a density, and this, lambda, is a linear density. And that's how many kilograms there are per meter, okay? So if we say this is a uniform density, let's say this lambda, it's constant. The density everywhere is the same. Well, we know the center of mass is going to end up in the middle, but let's prove that. So let's say it's a bar from 0 to L. And again, we don't care about this distance. I've just stretched it out. It's a very, very thin bar. Okay, so all I care is how dense it is, how much in a given little slice here of this length, dx, right? this lambda will be able to tell me how much the mass is. So let's go back. We always want to be looking at this dm business, right? So I'm going to say this thing, this little slice here has a mass dm. And I know lambda is the ratio of the mass per unit length. So lambda is dm over dx. And that means this dm is equal to lambda dx. Okay, so you can always start out with that definition of what that linear density is. It's the mass per unit length. But you always kind of want to move to this. The mass of this is just going to be lambda times how much length there is there. So if we want to find out the total mass, then what we want to do is we want to integrate. And remember that total mass is that bottom part that we need for the denominator. So we're going to go integrate from x equals 0 to x equals L of all the dm's, okay? But we know the dm's, we want to rewrite this in terms of these integration limits, which are going to be in the dx's. So let's substitute in lambda dx. So it's the integral from 0 to L of lambda dx. If lambda is constant, later we're going to have it where it's not constant, but if lambda is constant, that just ends up being lambda times the integral from 0 to L dx. Okay? So what we do, we integrate that and we get lambda x evaluated from 0 to L, and this ends up being lambda times L. Kind of a no duh here, right? Because if the linear density is how much mass per unit length, and we multiply it by the length, we get the total mass. So there's the denominator of our center of mass expression. Now let's find the numerator. So now let's find the integral from 0 to L of x times dm. And again, I'm going to substitute in for the dm. I really need to make sure that since I'm integrating across x, across that distance, I need this in terms of a dx. Well, that's just lambda dx, 0 to L. And I'm just going to go straight across here. The lambda is constant, so I'm going from 0 to x, x dx, 0 to L, x dx. This ends up being lambda times x squared over 2, evaluated from 0 to L, and that ends up being lambda L squared over 2. So then, to find my x center of mass is going to be integral of x dm over the integral of dm, and that ends up being lambda L squared over 2 divided by lambda L. The lambdas cancel, one L cancels, and you end up with L over 2. So what we've proven is that the center of mass is right in the middle of a uniform object. Now we can also do this if lambda is not uniform, okay? If lambda is something like lambda equals 5x, you can see that substituting that in here, we get a 5 and an x, and we have a much more complicated total mass and a much more complicated numerator. So this is the denominator, and this is the numerator that goes into the position of the center of mass.